Yesterday in class we went through and we discussed the states of matter from the solid phases to liquid to gas, the plasma. We also pointed out that there is a fifth state that was identified back in the 1920s by a guy by the name of Bose, later on confirmed mathematically by Einstein, and today, as Thomas pointed out yesterday after class, it's called Beck, B-E-C, which stands for your Bose-Einstein condensate. Okay, this is just as electrons lose their configuration, which establishes what the behavior and the properties of elements. At the very high end, because the electrons are physically knocked off of the material. Well, the same thing happens at the lower end as you approach absolute zero. There's not enough kinetic energy within the molecule or the atom to maintain its energy level. And so what happens then, it kind of falls out. You lose electron identity, and consequently you lose your properties then, and that was identified on that end. But I don't want to get into that today. We're going to look at, I want to put some numbers to what we had yesterday. We started out with a block of ice down here, and I assigned a temperature today of 20 degrees, minus 20 degrees Celsius, and we're going to use a 60 gram block of ice, which has been cooled down to minus 20 degrees Celsius. And we're going to take that block of ice, and we're going to input kinetic energy so it finally achieves still a solid block at 0 degrees Celsius. Then we're going to add in more temperature, more kinetic energy, and we discussed yesterday that as we add temperature, your ice, although it's melting in your drink's not warming up. The drink will stay the same temperature of that ice until it's all melted. So during a phase change from solid to liquid, there's no temperature change. The only thing we're changing is state. Then we go from liquid. Now as we continue to add more energy, we'll go from liquid at 0 degrees Celsius to liquid at 100 degrees Celsius, the boiling point. Once it starts to boil, there is so much energy in these atoms that they're bumping into each other, colliding, and at the surface of the liquid, occasionally someone gets bumped off the liquid. Okay? And we call that then vaporization. And if we continue to add energy, we will vaporize 100% of this liquid, all 60 grams of liquid that we started with. When the last molecule leaves, in a closed system, if we continue to add kinetic energy, then once again the temperature will begin to increase till eventually we hit the plasma phase. Okay? So starting at the very beginning, went through a little story yesterday about in the summertime when the sun's beating down on my back patio outside, concrete patio, grassy area, little swimming. I take a little pool out there, plastic pool I set up for my doggies. And in the summertime, at the end of the day, when it's hot, we like to go swimming together. We splash in that little plastic pool, the dogs and I. Only I don't want to waste time at the end of the day setting it up, so I set it up early in the morning. And at 6 o'clock in the morning when I set it up, the concrete's cool, the ground is cool, and when I fill the swimming pool, it's cool. Everything's nice and cool in the morning. 7, 8 o'clock that hot summer, it's been 100 degrees outside, the sun's been beaten down. At the end of the day, I step out onto the patio, getting ready to jump in the pool with my bare feet and burn the bottom of my feet. Get off on the ground's warm, step in the swimming pool, and it's still cool. So we established that nothing's changed, same amount of energy in the spot. This morning everything was cool, and tonight, concrete's hot, ground's warm, the water's still cool. And we attribute this to a thing called specific heat. Specific heat. And this is the amount of energy that has to be put in there to cause 1 gram of material to increase in temperature 1 degree Celsius. Okay? So, and here again, think about it now. Water, over 71% of our planet is covered with water. and it can absorb lots of heat from the sun and yet not change temperature a whole lot. A sister planet close to us, Mars, I guess you call it brother, Mars, even farther away, estimated that once upon a time had about 20% or less water. There wasn't enough water there to absorb the tremendous energy coming from the sun. Even though it's farther away, it was getting a little bit less. It's a little bit smaller planet. The earth part heated, the rock part heated up so rapidly, the temperatures increased, and a little bit of water that was there evaporated. If it wouldn't be for our surface of our earth covered with 71% of water, we probably wouldn't be here either. Because if it was all land, we'd get so hot and couldn't exist. Okay? So the concrete gets very hot. The ground is less, a little bit warm, and the water remains cool. Specific heat. The equation to compute specific heat, the amount of energy, Q, which is measured in joules, is equal to how much mass that we're doing times the change in temperature, and then we have a constant. And as I said, ground heats up faster than water. If I were to put on the patio deck out there a piece of steel and a piece of aluminum on top of the concrete, the steel would be the hottest, the aluminum would be a little bit cooler, the concrete a little bit cooler than that, the ground, and eventually the water. So the water is going to be the coolest. Has a very high specific heat. And the value of C for water, everything has its own value, 4.183 joules per gram degree Celsius. That is standard. Now, on exams, quizzes, questions, if I give you any other kind of material, I'm going to have to give you C. I'll have to give you that value. So that's not going to change as we do our computations. But you'll notice delta T, delta stands for change in. So this is a change in temperature. The only place we experience temperature changes when we go from a solid, we remain all constantly solid here, so we're changing temperature. Over here in the liquid, when we go from 0 to 100, we're changing temperature. In the gas phase, when we go from water vapor to plasma, we're changing temperature. In phase changes, we don't change temperature. They remain constant during phase changes. Okay, and we have two different formulas for those occasions. So let's begin first of all by working this one down here. And we'll start out. Q is equal to M delta T C. Q is what I'm solving for. How much energy is it going to take to change the temperature of this ice from minus 20 degrees Celsius to 0 degrees Celsius? It's still going to stay ice. Okay? Just I'm changing the temperature of the ice. Mass, I have 60 grams. Change in temperature, minus 20 to 0. It's going to be changing. At this time, the signs aren't really critical, the direction. 20 degrees Celsius is what I'm changing. And my constant, 4.183 joules grams degrees Celsius. Okay? Notice the units. Always pay attention to your units. They'll keep you straight. Grams are on the top part. I can reduce them out. Grams are underneath. Degrees Celsius on top, underneath. So once I crunch all these numbers, I'm going to end up with some value in joules. And that's what I'm looking for. So my Q is going to be equal to some value in joules. So we push buttons. 60 times 20 times 4.183, and that should be equal to 5019.6. Okay? 5019.6. Save that value. We're going to come back to it. Okay, we did that one. We're also changing temperature when we go from liquid at 0 to, yes ma'am?
Can you tell me again where you got the 4.183?
It's given. That is a standard for water, whether it's water solid, liquid, or up here vapor. That is a standard specific heat value. Okay, and if I made this, I could have done this in aluminum. Okay, Only up here then we'd have 1.9 something. I don't remember what aluminum was anymore. I'd have to give you those values. Okay, getting back to this again. We're going to go from liquid 0 degrees Celsius to liquid at 100 degrees Celsius. Okay? So using our formula, Q is equal to M delta T C. My mass, still 60 grams. Delta T, I'm going from 0 to 100. So my temperature is changing by 100 degrees Celsius. And my constant for water, 4.183 joules grams degrees Celsius. Again, reducing out my terms. And then I can math. Now if you're, 60 times 100 times 4.183, and that's equal to 25098. Yeah, 25098. And since that answer over there was in tenth, I'm going to keep ours in tenth, and that's joules. And again, save this one. We'll need it. And for class purposes, once we get to the vapor state in a closed system, I'm going to go ahead and keep, I'm not going to take it all the way to plasma since it's not really defined. Okay, quickly, have a seat. We're going to compute it, what it would take up here, and we're going to go to 350 degrees Celsius. We're going to increase the system to 350 degrees Celsius. So then, using I got to determine what energy it takes me now to get it from 100 degrees to 350 degrees Celsius. So Q is equal to, let me do this part down here. Q is equal to M delta T C. So Q then is going to be equal to my mass, 60 grams. Change in temperature from 100 to 350, I'm changing 250 degrees Celsius. And water vapor, 4.183 joules grams degrees Celsius. Okay, reduce my units. And 60 times 250 times 4.183, and that's equal to 62745. 62745, and again keeping our answers in tenths, and this is in joules. Okay, we'll save this one. All right. Those are all the places that actually change temperature. Now we have to consider places where we're changing state. We're going from a solid to a liquid, from a liquid to a gas. And the rules change a little bit. We have some in physics. There's a term called, let me pick a nice color here, enthalpy. Of, in this case, fusion. Okay, enthalpy of fusion. This is the amount, enthalpy simply means the amount of energy that is required to change 1 gram of substance, or is required to change from the state, 1 gram of substance to change state. Enthalpy. Fusion, melting, freezing. If I'm going from solid to liquid, it's melting. If I'm going from liquid, I have to remove this much energy in order to get it back into the solid state. So I don't have a temperature change involved. Temperature remains constant. So my formula for this one then is my enthalpy, which is measured in Q, energy, is equal to the mass, and the symbol for enthalpy is H, and in this case, fusion. Fusion. Enthalpy of fusion. The constant value for that. For water, again, water has a constant value. If it were aluminum and I'm going from solid to liquid, it would have a value. Okay? So everything has its own individual value. And the value for this one is 334 joules per gram. Constant for water. Okay? So to compute this equation then, all we needed to, we take my Q, what I'm solving for, how much energy, is equal to my mass, 60 grams, times my enthalpy of fusion, 334 joules per gram. Again, notice your terms. Grams on top, grams on bottom. And we do the math at this point. So we take 60 times 334, and that's equal to 20,040. 20,040.0 joules. That one. Hold that. Okay. One more to go. Okay. So now we will come over here. Here again, we're changing state from liquid to gas. I'm not changing temperature. Temperature remained constant, 100 degrees Celsius. Enthalpy of vaporization. Q is equal to, again, my mass, enthalpy H, only now it's sub V for vaporization. Okay. Solving for the amount of joules that we're required to do this, Q is then going to be equal to my mass, 60 grams. Didn't give you the value. Enthalpy of vaporization for water, I got to check. What did I give you? Didn't have that up here. What did I give you yesterday? 22 what? On your sheet. 2264. Okay, 2264, and this is going to be joules per gram. That's our constant. Okay, so then we multiply this times 2264 joules per gram. And math, 60 times 2264, and that's equal to 13,584. 13,584.0 joules. And that's this one. And so the question then, how much energy does it take totally to melt 60 grams of ice at minus 20 degrees Celsius and get it to the vapor state at 350 degrees Celsius? So now you have to add up all these values that we computed. So we start over here in my first phase. And Q was equal to, let me back up here a little bit. Q is equal to 5019.6. Second phase, 20040.0, and this is all in joules. Third phase, 25098.0. Fourth phase, big one, 135.843. Is that one correct? I think, because that should be a very large number. Let me double check. 60 times 2264, 13580. Oh, I have the decimal. 0.0. Thought it looked bad. Okay. 135,840.0 joules. And then my last one, 62745. 62745.0 joules. Now if we add all those up, okay, 5019.6 plus 20040 plus 25098 plus 135840 plus 62745, and that should be equal then, the grand total is 248,742.6 joules. That's how much energy is going to be required to accommodate that conversion of the ice at minus 20 degrees Celsius to steam at 350 degrees Celsius. Now, a couple interesting points here, if you'll notice. Low joules over here to melt or freeze ice. But look at the comparison to make steam. Okay, the amount of joules. It's almost 5 times the amount. For people that have inadvertently burned their hand in boiling water, got red. But some people, if you've ever burned your hand with steam, keep in mind it's about 5 times hotter than boiling water, simply because of the amount of energy required to make steam, to put enough kinetic energy into that system to actually beat the molecules off the top of the water. Okay? All right, questions? Huh? Burned yourself with steam? That's not nice. Any other questions? And that concludes the lecture for thermal kinetics in states